We already know that any problem involving the distribution of charges can be solved by breaking the charge distribution into a series of point charge and then either integrating or summing the individual point charge contributions. We did this with electric fields, and the difficulty there was that in the integrals, or the sums, depending on whether you had continuous or discrete charge distributions, you had these unit vectors, r hat, that made those quite difficult. With electrical potential, we avoid that because we're adding scalar quantities. So in order to work these problems, we're going to need to know the electrical potential for a point charge. Now again, really only the difference in electrical potential has meaning, as I've said in the other videos. So we have to note that when we do this, that there had to be a reference point, and that reference point was at r equal infinity. So a formula that you need to definitely memorize is that the electrical potential for a point charge Q is kq over r, where r is the distance from the charge to the point that you're trying to find the electrical potential at. Or if you prefer, 1 over 4 pi epsilon naught times q over r. The advantage is there's no r hat. But since I don't have a delta v here, that means I must have been choosing a reference point, and the reference point in order to get this nice looking formula is r equal infinity. And I will show that now. So to derive this formula, I'm going to start with a object setting right out here, and I'm going to move that, or think about moving, all the way into where this x is located at a distance from my charge of r. Now, this says that the change in potential is the negative of the integral as I move from infinity to r of the electric field dotted into the displacement. But how do you write the displacement in spherical coordinates? Well, that's what we want to know. So let me write the things that we need to do here. The electric field I need to have for my point charge. I know that from the previous chapters. It's kq over r squared r hat. And that r hat is in spherical coordinates. The displacement vector, in general, could be written as dr is equal to dr r hat plus r times the differential of r hat. However, let's look at this. This is, you stay along r and you change the length of the unit vector, or the vector, in this case r. The second is that you don't change the length, you change the direction. But when you change that direction, that change is perpendicular to the vector, this unit vector that you're changing. Well, this, when I dot it into r hat, will go to 0 anyway. But since this is in fact a case of a conservative force, I could choose any path, and I chose to move the path right along the radial vector, where r starts at the q and goes outward. So that means that there is no dr hat in my problem because of my choice of path. So my differential is just dr r hat. But even if there was, the dot product with this r hat would still create no contribution to the problem. Now to find the potential, I have v of r minus v at infinity is equal to minus the integral from infinity to r of k q over r squared dr. Now there's a tendency of students, when they say differential, they say, hey, whoa, 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 aren't we coming in the negative r hat direction, and so shouldn't I put a minus in this dr? No. That minus sign about the fact that you're coming along the negative direction, that is reducing the radius, is already accounted for in integrating from infinity to r. If you put a minus sign in the differential, you'll have actually flipped these limits and messed it up. Okay? You just write the same differential in spherical coordinates every time. Doesn't matter which way you're moving. The limits will take care of it. Now, the k and the q can come outside. And I have an integral from infinity to r, 1 over r squared dr. This means v of r minus v of infinity. I can do that integral. I get minus kq, and then I get minus 1 over r, evaluated from infinity to r. The minus and the minus will cancel, so I get kq over r when I put in the first limit, minus kq over infinity, which is simply 0. If I now make my zero potential energy reference point be at infinity, if I make this be 0, then I have that v of r is kq over r. And that's why he chose the way he did in the book. Now, once I have this formula, I can extend this to dealing with non-discrete point charges as well as discrete point charges. For discrete, you just simply add up the contribution for each point charge, so you get sum of I equal 1 to n times V sub I, that is the voltage for each charge, which is simply the sum of I equal 1 to n of k, the charge, divided by the distance r sub I. So this is like k q1 over r1, k q2 over r2, so on and so forth. If you've got a continuous set of charges, you do something similar to what we did with our integrals for the electric field. V is equal to the integral of k dq over r, and we're doing that over all charges. Now this looks very much like the integral that we had for the electric field, but we don't have that vector r hat, and that is a tremendous savings. We don't have to find r hat, we don't get the trig functions bouncing into it, and often these integrals are much simpler. And even if they weren't simpler, if you'd broken this to ijk, you would have had to do an integral for each component of the vector, whereas here we only have one integral to do. Now, the next thing I'll do in the next video is I'll actually do some example problems.